Hello everybody. So this is a continuation of the magnetic field around a wire, and now we're doing a single loop. So because of the shape, the magnetic field that we're calculating is actually the one that occurs in the middle of the field, where the wire one would be, if we were at some distance, we'd be talking. Because what happens inside a loop and multi-loops is the field points the same direction and combines, and it actually causes a dipole. And we're going to go through the drawings to explain. You saw the compasses line up, you saw them move. All right, so let's start with the formula. The magnetic field of the loop is K sub 0, or K naught is what it's usually said, times the current divided by the radius of the loop, and the field again will be in Tesla. So if I'm going to calculate the strength of the magnetic field inside a loop, so we're going to start with a single loop. I'm going to have 10 amps and a radius of 0.05. So let's do it. Magnetic field is going to be, now this can be a little tricky on the calculator. I tend to, instead of putting in 2 times pi, it actually just depends on which kind of calculator you're using. We'll try it on mine, on the TI. There are some that don't respond well to that. So let's just set it up. 2 pi is 10 to the negative 7 times the current. Let's see, the current was 10 divided by 0.05. That's about how many amps? That single loop that I showed you in the demonstration that was here with the compasses, that's probably close to 5 centimeter radius, and I was probably getting 10 amps on that pretty easily. All right, so let's just try this. 2 pi second EE negative 7 should work, times 10 equals divided by 0.05. We're getting 1.25 times 10 to the negative 4 Tesla, and 1.26. It is correct. So you can put in the 2 pi. There's certain, it's Casios that don't like that. If you're using a Casio, they don't always like that. All right, so let's jot that down. So the magnetic field strength is we'll do 26 times 10 to the negative 4 Tesla. Remember, the Earth's magnetic field on average is about 5 times 10 to the negative 5th Tesla, and this is definitely stronger than that. So let's talk about the hand rules that go with this. So this is a nice 3-dimensional picture, and basically what's happening is current is going up and then it's going down. That's a 3-dimensional picture. That's not so easy to necessarily, what's the word I'm looking for? Draw. So instead, just excuse me for a second, I'm going to take my little loop here of wire, try to put it in front of the camera so you can see it. So we're going to look at it from the top view. So if current is coming up means it's coming at me, that's a dot, and it goes over and goes down the other side, that means it's going away from me. Dot is up, X is going away, is down. All right, so first case, we'll do dot X. Draw a circle. Draw a circle. Remember when I showed you, the arrows showed the same way. We're going to use, since we're doing current, right hand rule, it's still curled. X is down. My fingers are curling clockwise. So always please put 4 arrows. These arrows represent those 4 compasses. That's exactly what they are. Dot. My thumb is up. My fingers are curling this way, which is counterclockwise. Again, 4 arrows. Notice inside the arrows are in the same direction, just like the demonstration. All right, I'm just going to reverse it. If I have the X over here and the dot, and that's really the only choices you have, draw a circle, draw a circle. Well, I should memorize these, right? But I don't. I use my hand rules. All right, so this one's going to go this way, and the other one's going to go reverse now. 4 arrows representing. So here's what's going on in the middle. Inside the middle, there is a magnetic field, and it points the same way as the arrows. So this one points up, this one points down. As a matter of fact, let's give it, at this point, it's an air magnet. It's an electromagnet. It's magnetism in the air. And if I would like to make that stronger, I'm going to put some metal in there. You can imagine, even though I'm going to use a dotted line when it's not a real magnet, basically, dot, 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 inside the coil is an electromagnet. And I'm making this as if it was like a bar magnet. Now, this end, which has the tail, is the South Pole. This is not pointing to the north, I am labeling the north. The arrow gets a north. Same thing in this picture. The arrow, that side is the North Pole, this side is the South Pole. So when Ørsted figured out that electricity causes magnetic fields, the next step was literally just changing the shape of it, and inside you actually get a true electromagnet. That's why the field inside combines to make magnetic poles. Not just a magnetic field, it actually is a dipole. Now, if you simply wrap wire, I mean, I could do this. I could take and put this on my hand and just wrap it, and wrap it, and wrap it, and keep wrapping it. It's a really janky wrap, but, okay, so that's a really ugly coil. But I can put electricity on it, and whatever happens inside is now 1, 2, looks like 5 times stronger than if I did it once. That's what's called a solenoid. Solenoid, lots and lots of coils wrapped on a tube, and most solenoids will have metal in the middle, but they don't have to. Oops. Formula. It's the same as the loop, except there's a multiplier of the number of coils. So it's N, K sub 0, I over R. And again, it's going to create stronger fields. If you go to a junkyard, they have an electromagnet. It's a giant piece of metal in there with a lot of wire. We actually have electromagnets on the back of all of the doors in the school. If you see those things where you push up against the door, they are set up to electricity. They're electromagnets, and when the fire alarm runs, they close. All right, so let's do this one. Let's figure out the magnetic field. So B, so 540 is the number of turns. K naught, or K sub 0 is 2 pi times 10 to the negative, that's a 7, times the current, which in this case is now 3 amps. Sorry, I'm double checking something. And I've tried not to give you any conversions here. All right, let's do this. All right, so 540, that helps if I turn it on, clear. 540 times, I'm gonna throw parentheses around this, 2 pi, second E, negative 7, times 3, divided by 0.02. And there you go, 0.05 is all we're getting. 0.05 Tesla. And yes, Tesla gets a lot of credit for a lot of electricity and magnetism related types of topics, not just electric cars. So, as soon as you have a solenoid and you have all those loops, things happen. First, the field inside combines more. Between the fields, in between the wires, the fields cancel. And outside the field, it looks as if there was a bar magnet. Okay, so here is a stock kind of picture. And I want you to realize that this is sort of a 3D version. You see where there's an X here, and a dot here, an X here, a dot here. So you have to imagine that, let's see, if this was current, let's see, that's my X. Yep. So electricity is going away from me here, towards me here, away from me here, I guess it's going this way, towards me here, starts here, away, towards, away, towards. I know it's hard because it's 3-dimensional. We don't draw the picture like this. It's a little hard to do. It's sort of like this. If I put this in front of me, think of it like this. Electricity is going to go around, right? So on this side, it's going to come towards you, away from you, towards you, away from you, towards you, away from you. Every time I come up, it's towards you. Every time I go down, it's away. And so remember, if it comes towards you, It's a dot. So we're going to pretend like it was this one, this case. Towards you, away from you. Towards you, away from you. So all of the towards will be on the same side. Let me move this. All of the aways will be together. We generally use 3 dots, or 3 circles. All right, make a circle around each. Try not to let them cross. Okay, so it's pretty easy. Dots. My hand is up, my fingers are curling. So 4 arrows. 1, 2, 3, 4. 1, 3, 4. And of course, X, my hand is going to go like this, and they're going to go clockwise. So squeeze them in there. Yeah, there's going to be a lot of drawing in this unit, if you didn't already figure that out. Now, inside. I said the inside combines. Do you see every one of these arrows on the inside? They all point to the right. So I'm going to use my highlighter and I'm going to draw one line. I'm going to put the arrow the way that they're all facing, which in this case was to the right. It is an electromagnet. I'm going to make little dotted lines. Okay, the tip part becomes the North Pole. The tail part becomes South Pole. Again, if you were to follow these, everything on the inside combines. The part up here where it says between the wires, the field cancels, well, look right here. This would be between the wires. One's up, one's down. One's up, one's down. One's up, one's down. They cancel. There's no magnetic field happening there. It's only in the center and on the outside. Because if I follow all of those arrows, they all point to the south. See, the arrows are still the same as if it was a bar mix. Sorry, these are a little messy. Which matches that one, and that's how this picture becomes. So this is our 2-dimensional picture to show how you would find the north and the south pole of a solenoid. All right, we're going to practice more of these. Bye now.